Welcome to lesson 6.5 and 6.6. We're going to be looking at theorems about roots of polynomial equations and the fundamental theorem of algebra. Okay, well, what does all that mean? If we look at the objective, we're going to solve polynomial equations using the rational root theorem. That's the first thing we're going to do. Well, I guess the first thing we'll do is understand what the rational root theorem is, but it is going to be used for solving polynomial equations that can't be factored the way that we learned in previous lesson. And you can graphing only works so well. If it's irrational, you're only going to get a rounded answer, and if it's imaginary, you're not going to be able to see it at all. So graphing is not foolproof either. So this is a method that we can use to solve for equations that we haven't been able to solve yet. And then we'll look at those other theorems as well. All right. We will be using calculators. So we're not doing this totally by hand. And I'll show you how we're going to use graphing to aid in the process of this. So the first thing we're going to do is define the fundamental theorem of algebra. To make sure you know how many solutions each polynomial equation will have, you use the fundamental theorem of algebra. And that is that the number of roots each polynomial equation has is equal to its degree. So, for instance, a third degree polynomial will have 3 solutions. Fourth degree will have 4 solutions, and so on. That's the fundamental theorem of algebra. All right, the rational root theorem. I'm going to read it. It's not going to make sense, and then we'll unpack it. Okay. So the rational root theorem, if P over Q is in simplest form and is a rational root of the polynomial equation with integer coefficients, then P must be a factor of the constant term and Q must be a factor of the coefficient of the highest degree term. Okay, so what does that actually mean? So if a polynomial has a rational root, it has to come from a combination of the factors of the constant and the leading coefficient. It can't just be a random number. It won't just be a random number. So that's not to say that every combination of the factors of the constant and the leading coefficient will be rational roots. It's just saying if it has a rational root, it will have to come from that group of numbers. So essentially what we'll be able to do using this theorem is narrow down all the possible rational roots of any equation before we start solving. So the first step here is to list out the factors of each of those things. When there is no number, remember the coefficient is 1, so the factors of 1 are plus or minus 1. For the constant, the factors of 8, you have 1, and you have 8. I always think of them as in pairs, right? So 1 times 8 is 8. Another factor pair would be 2 and 4, so plus or minus 2, plus or minus 4. And it's plus or minus because negatives could be factors too, like negative 2 times negative 4 would be positive 8. All right, so what that means is possible but not guaranteed rational roots are all of these numbers, factors of 8, divided by all of the factors of plus or minus 1. The nice thing about dividing by 1 is it's all the same. So the possible rational roots are plus or minus 1, plus or minus 2, 4, and then 8. I'm just writing them in numeric order now. Now we're going to test each possible root by substitution or synthetic division. So you have those two options. I'm going to do synthetic division. And then we find the roots of the quotient. So what you can do is start testing using synthetic division. If it is a root, you'll get no remainder. If it's not a root, you'll get anything else as a remainder. So if I look at the equation, so what we're going to do is synthetic division with one of these numbers. There's 8 possibilities, right? Because plus or minus 1, 2, 4, and 8. So let's try positive 1 first. And then we have 1, negative 4, negative 2, and 8 are the coefficients. So we drop the 1. 1 times 1 is 1. We add down, we get -3. 1 times -3 is -3. We add down, we get -5. 1 times -5 is -5. We add down, we get 3. So that means 1 is not a rational root, even though it was possible. So now we're going to try something else. Let's try 2. So we drop the 1. 2 times 1 is 2. We add down, we get -2. 2 times -2 is -4. We add down, we get -6. 2 times -6 is -12. We add down, we get -4. So again, 2 does not work. Let's try +4. So we drop the 1. 4 times 1 is 4. We add down, we get 0. 4 times 0 is 0. We add down, we get -2. 4 times -2 is -8. We add down, we get 0. So what that means is 4 is a possible rational root. Now that we know that 4 is a possible rational root, that means one of the roots is x equals 4. So I'm going to write that there. What we can do now is take the equation that we got from dividing. So -2 is a constant, so -2. 0 is linear, so there is no linear. And then 1 represents my quadratic, so I have x squared minus 2. I'm going to set that equation equal to 0. Now I can add 2 to both sides, and you get x squared is equal to 2. Take a square root of both sides, and you get x is equal to plus or minus square root 2. So those are the other two solutions, or roots. In other words, you could also write it as, and if you notice, we have 1, 2, 3 solutions, and the equation was a cubic equation to start. So that is demonstrating the fundamental theorem of algebra in that we got 3 solutions from a third-degree polynomial. We're going to do the same thing. This is basically the same kind of question. I'm going to throw in one thing that might help you do it a little faster. But we're still going to list out the factors of 1, so plus or minus 1. Factors of 10, plus or minus 1, and plus or minus 10. So because 1 times 10 is 10. Also 2 times 5 is 10. So those are the possible factors. We have plus or minus 1, 2, 5, and 10 as the possible rational roots. Instead of just blindly testing like we did in the previous example, let me suggest doing this. I would graph the equation and see if you can see where it's crossing at one of these possible rational roots, and then use that. Like, that'll guide your decision of what to try for synthetic division. We'll still have to do synthetic division. We'll still have to solve the quadratic that you get out of it, but at least it can narrow it down and we're not just blindly checking. So I'm going to go to Desmos. To graph, you can graph however you want to graph. Equation is x cubed minus 2. Minus 5x plus 10. This one appears to be crossing at 3 places, which makes sense because we have a third degree. That just means all 3 are at least real. But if I look, that is not one of our possible rational roots, right? Neither is that. But this one is. So it looks like there's one rational root, because 2 is from our possible rational root list. The other 2 roots must not be rational. They must be irrational. So that's something I can tell from looking at this graph as well. But what this is telling me is I'm trying 2 with synthetic division first, instead of just blindly guessing. So we're going to put 2 in the box, and then the coefficients go 1, -2, -5, and 10. So we drop the 1. 2 times 1 is 2. We add down, we get 0. 2 times 0 is 0. We add down, we get -5. 2 times -5 is -10. We add down, we get 0. So that confirms what we thought by looking at the graph, which is that x equals 2 is one of the roots. Now we can take what we get from there, x squared minus 5 equals 0. And we solve that one. We're going to add 5 to both sides, and we get x squared is equal to 5. We take a square root of both sides, and we get x is equal to plus or minus square root 5. And again, we got 3 solutions. This is a cubic function, so that makes sense. You may encounter examples where when you get to this point, you need to use quadratic formula. That's possible. You may get to this point and you can solve by factoring, whatever, but you're going to get a quadratic that you need to solve like you did in chapter 5, one of those ways. So it might not be solving by square roots like this part was. It might be quadratic formula. It could be solving by factoring, that kind of thing. All right, second part of the objective. Now we're going to talk about irrational root theorem and then imaginary root theorem, and they are very, very similar. First thing we're going to talk about is this definition of the word conjugates. They are number pairs of the form a plus square root b and a minus square root b. Notice how the terms a and square root b are the same. The only difference is the sign of the irrational part. And we are defining square root of b as an irrational number. So the irrational root theorem states, let a and b be rational numbers, and let square root of b be an irrational number. If a plus square root b is a root of a polynomial equation, then the conjugate a minus square root b is also a root. So if you know that an irrational number is a square root, its conjugate is also a root. That is what this theorem is saying. So if it says find additional roots, and you're given that 5 plus square root 2 is a root, then 5 minus square root 2 is also a root. That's all this is saying. If it's a monomial, it works very similarly. If negative square root 6 is a root, then square root 6 is a root. 4 minus square root 3, if that's a root, 4 plus square root 3 is a root. And if 8 minus square root 7 is a root, then 8 plus square root 7 is a root. This is not a trick, it is really that simple. The imaginary root theorem works very similarly. In this case, they are complex conjugates. So if a plus bi is a complex number, a minus bi is its conjugate. The imaginary root theorem states, if a plus bi is a root, then its conjugate a minus bi is also a root. So we are going to find 2 additional roots for these. If 2 plus 9i is a root, then 2 minus 9i is a root. And if it's a monomial, it's just the opposite. So if 7i is a root, negative 7i is a root. All right. So example 4 here says write a 4-3 polynomial equation in factored form with roots 2 plus 9i and 7i. So the ones that we just looked at. Remember that if 2 plus 9i is a root, 2 minus 9i is also a root. If 7i is a root, negative 7i is a root. Notice how there are 4 total roots, and it's asking us to write a 4-3 polynomial. So that makes sense. We have all the roots. Remember the factor theorem from a previous lesson. The factor theorem states if you know a root or a zero or a solution, whatever, all the same, then x minus that root is the factor that it came from. So let's just start with 7i. If 7i is a root, x minus 7i is also a root. If negative 7i is x minus 7i is the factor. If negative 7i is a root, then x minus 7i or plus 7i is a factor. When it's a binomial, you just got to be careful. You got to put parentheses in parentheses. What I mean by is if 2 minus 9i is a root, then x minus 2 minus 9i is a root. And then if 2 plus 9i is a root, then x minus 2 plus 9i is a root. That is the polynomial in factored form. So if that's what it's asking for, that's it. If it asks for it in standard form, you would need to multiply all this together. All right, part B here. Notice how this is saying a fifth degree. We've got three roots, 5, 1 minus root 3, and root 10. 1 minus 3i, I'm sorry, 1 minus square root of 3, I should say. 1 plus square root of 3 is the conjugate and also a root. If square root of 10 is a root, negative square root of 10 is a root. But there is no theorem for a rational number like this. So there is no conjugate of 5, there is no additional root. So you're not, like negative 5 is not a root because 5 is. This is a fifth degree polynomial, and that's a clue that also you're not getting an additional root out of that. So these are your 5 roots. So it's x minus each of the roots. So x minus 5, x minus root 10, x plus root 10, x minus 1 minus square root of 3, and x minus 1 plus square root of 3. And that's it. So we're going to practice this, try the exit ticket. We will go over the exit ticket together and then start the practice. Let me know if you have questions.